Hello everyone, welcome to another hands-on engineering tutorial. In this lab, we're going to be going over the MUX. Microcontrollers are often used to interact with numerous sensors and other devices. All of these interactions are handled via the digital and analog pins on the Arduino. There are a decent number of pins available, but sometimes there just aren't enough to complete the project. You'll find that it's surprisingly easy to run out of pins on complicated projects, especially if you're working with many analog sensors. There are several ways to overcome this problem, and we'll go over one such solution in this lab. A MUX is one tool that lets us add additional inputs to our microcontroller. MUXes are devices with some number of inputs that can be conditionally connected to just one output. By manipulating the control bits on the MUX, we can decide which of those inputs is connected to the output. Only one input is connected to the output at any particular time. By connecting the one output of a MUX to the Arduino, we can gain several inputs. The MUX we're using has 8 inputs. The 8 input pins are labeled Y0 through Y7. The output comes from the Z pin. The pin for power is VCC, which will be 5 volts, and at least one of the ground pins in the MUX should be connected to the ground on the Arduino. The last pin of note is the E-bar pin. E-bar is the enable pin, which is active low. This means that it needs to be connected to ground to enable the device. If E-bar is connected to 5 volts, or left floating, then the MUX will not work properly. The select pins on the MUX are what control which input is connected to the output. On this MUX, they are labeled S2, S1, and S0. The combined binary value of the select pins determines which input pin is connected to the output. This MUX has S2 as the most significant bit, and S0 as the least significant. This means that all 3 of the pins have their binary value combined into one larger number, in the order S2, S1, S0. The table on screen shows the decimal equivalent of all 8 possible combinations. You may find this table especially valuable if you are unfamiliar with converting between decimal and binary. The decimal equivalent corresponds to which input pin is connected to the output. For example, let's say S2, S1, and S0 are 0, 1, and 0 respectively. According to the table, we have a decimal value of 2. This means that the input Y2 is connected to the output Z. None of the other pins are connected to Z. Measuring the value at Z will let us know what the voltage is at Y2. We only need 3 digital pins and 1 analog pin to use the MUX. This means that the MUX gives us a net gain of 4 inputs. In addition, all of the inputs that are fed through the MUX can be analog. Thus, we are really gaining 7 analog inputs at the cost of 3 digital pins. This demonstrates that MUXes are incredibly valuable, especially when a project is running short on usable analog pins. We'll be using the accelerometer that we went over in Lab 2 to demonstrate how the MUX works. Make sure to check out that lab if you haven't already. Let's go over the circuit to see what it looks like on a breadboard. This is our circuit. We have our Arduino Nano, an accelerometer, and the MUX, as well as a ton of wires to connect all the devices. The accelerometer's VCC pin is connected to the 3.3 volt voltage line on the Arduino. The ground pin is connected to the ground on the Arduino. We connected the X, Y, and Z acceleration outputs to both the MUX and the Arduino so that we can compare the values seen on the Arduino to the ones shown in the MUX to make sure that the MUX is working correctly. For the Arduino's connection, we connected X, Y, and Z to A1, A2, and A3 respectively. On the MUX, we connected X, Y, and Z to Y0, Y1, and Y2 respectively. The MUX's power comes through its VCC pin, which we connected to 5 volts on the Arduino. We also connected the ground pin on the MUX to ground on the Arduino. E-bar is connected to ground as well. The control bits S2, S1, and S0 are connected to D6, D5, and D4 on the Arduino respectively. The output Z of the MUX is connected to the Arduino as well, to A0. That's all of the connections, so now we can go over our code. This is the code we'll be using. We begin it with a bunch of constant integers for all the pins that we connected to on the Arduino. MUX pin corresponds to the output of the MUX, which we connected to the Arduino. We connected it to A0, so we set it equal to 0. X pin, Y pin, and Z pin are for the accelerations that are output from the accelerometer directly. We connected the x-axis to A1 on the Arduino, which is why it's 1. The same logic applies for pins Y and Z. S0, S1, and S2 are for the control bits on the MUX. We connected S0 to digital pin 4, S1 to digital pin 5, and S2 to digital pin 6. Inside of setup, we begin serial communications at a baud rate of 9600. We use pin mode on S0, S1, and S2 and set them all to outputs because we want to be able to control the MUX from the Arduino. We conclude by using digital write on S2 and writing low. That's because we want to only read from Y0, Y1, and Y2. And for all of those, S2 is always low, so we're just writing low here and then forgetting about it. Inside of loop, we use digital write on S0 and write low, and then do the same thing for S1. This means S2, S1, and S0 are all low, or 0, which means we're reading from Y0, which we connected to the X output of the accelerometer. We have a delay of 1 millisecond here to make sure that there's enough time to switch on the MUX. This isn't strictly necessary. It's just to guarantee that the MUX switches in time. The switching rate of the MUX is usually so fast that this isn't necessary. We read the DirectX analog input from X pin. This means we're getting the output directly through the Arduino. After that, we read the output that's from the MUX. After that, we use digital write S0 and write high. Now we have 0, 0, 1, which corresponds to Y1 on the MUX, which we connected to the Y output of the accelerometer. We have that same delay of 1 millisecond, and then we read the direct Y value, and then the value from the MUX. Now we wrote S1 to be high, and S0 to be low, so now we have 0, 1, 0, which corresponds to Y2. We connected Y2 to the Z output of the accelerometer. We have that same delay of 1 millisecond, and then we read the Z value directly from the Arduino, and then the Z value from the MUX. Now that we've read everything in, we can print it to the serial monitor. We printed DirectX, and the DirectX value. This is the value that was directly read from the Arduino. And then the MUX value. We also space things out a little bit, so that it's clear when you're looking at it on the serial monitor. You'll see what we mean when we actually demonstrate it. We do the same thing for Z as well. Make sure that the last one has an ln at the end, so that the values are spaced correctly. We then conclude with a delay of 100 milliseconds, so that we're not being bombarded with information at too quickly of a rate. Alright, let's see what the code looks like. Open our serial monitor, and as we can see, we have DirectX followed by muxx in the first column. The second column is DirectY and muxy, and the third column is DirectZ and muxz. Let's turn off auto scroll and compare the values. DirectX and muxx are both the same. DirectY and muxy are very close to one another, but not exactly the same. This slight difference is understandable because the input signal might change very slightly in between these two measurements, causing these slight changes in value. DirectZ and muxz are also the exact same. Now let's see what it looks like when we actually turn the device. So let's put it at an angle, turn off. We have DirectX is 312, muxx is 320. This slight difference is understandable because maybe these two measurements were taken very slightly after one another, causing our measurement to be slightly different. Same for the difference between Y and for Z. I bet if we just held it again, yep, it didn't move, barely moved, so now all these values are exactly the same. We must have gotten it when we were slightly shifting it still in between the two measurements. Let's put it in a different angle. Hold it. There we go. We got 380, 379, 299, 300, and 401, 401. Thus, we are certain that the MUX is working correctly because these values are very close to one another. The values within the same axes show the same trend of increasing or decreasing. Even if the values aren't exactly the same due to the slight time delays, we are going to see that the values are very close. Of course, these time delays won't really exist when you're using the system because you won't be measuring through both the Arduino's analog pins and through the MUX, so this slight error actually doesn't matter. It's only a thing when you're trying to compare to see if the MUX is working properly. Since we know how to implement the MUX properly now, we can include it in some of our later projects. Some of these later projects are very complicated and involve a lot of inputs, and that's why the MUX will become very valuable. That's it for this lab. We hope you learned something new about muxes and how we can incorporate them into our projects. As always, if you enjoyed the video, make sure to leave a like and subscribe to our channel. If you have any questions or recommendations for what we can show during our videos, leave them in the comments below. We'd also appreciate video suggestions in general on future topics we can cover or projects that we can build. That's it for Hands-On Engineering. See you next time.